Okay, welcome back, everyone. I want to start today with just a few remarks on a topic that we have been kind of skirting, which is the discussion of eigenfunctions of the Laplacian as opposed to just harmonic functions. And one reason I want to do this is I want to give some feel for what these eigenfunctions look like and the mathematics that's involved. And also they play a role in diagonalizing the Laplacian and therefore writing down the Green's function. So let me remind you how the Green's function works, say on a Jordan disk. The idea is that the Green's function should be an inverse to the Laplacian. So if you take the Laplacian of the Green's function of some function c, you should get c itself, and c restricted to the boundary of omega should be 0. Let's say in the case where c is a c infinity function. Now, it turns out that a good way to try to write this down is to let Fn be an eigenbasis for the functions, well, for the Laplacian on functions on d bar with the property that Fn restricted to the boundary of d bar is equal to 0. And what I mean by this is these functions should satisfy Laplacian of Fn is lambda n times Fn. Their integral of their norm squared should be equal to 1. And this is respect to the Euclidean metric. So we have chosen a metric here. And of these, and then per force, they're orthogonal to one another if they're distinct, come from distinct eigenvalues. And then we write our function c as the sum of an Fn. And then the inverse of the Laplacian applied to c would just be the sum of an times lambda n inverse times Fn. So, and morally, this is the same as the Green's function applied to c. And so the expression for the Green's function can be found as soon as we know what an is. But since these are orthogonal, an is just the integral of c times Fn. Everything is real here, so I don't need to introduce a bar. And what that means is the upshot is that g of zw can be written as the sum of lambda n inverse f of z, fn of z, fn of w. So when you take the integral of g of zw against c, say of w dw, what comes out is you integrate fn of w against c of w, and out comes an, and then you get exactly what we wanted, the sum of lambda n inverse and fn of c. So that is the kernel for the Green's function, and it's manifestly symmetric in the arguments. That was one of the things we saw in the case of the disk. And that's one of the reasons why it's of interest to know what these eigenfunctions are. There's many other reasons, but what I want to just give you a glimpse of is what these eigenfunctions look like in the simplest case in 2 dimensions, which is the unit disk. So before I do that, here's a sociology question for you and for me. How many people here, raise your hand in using the raise hand reaction, if you've seen Bessel functions in a class or in a book? Okay, so far 4 people. Oh, wow. Okay, so 5 people have seen Bessel functions. Whoa, whoa, whoa. Okay, that's great. So almost half the class has seen Bessel functions. Can somebody tell me what Bessel's differential equation is? Say for the simplest Bessel function, J0. Maybe one of the people with their hands raised. Alec, you were awfully quick to raise your hand. Do you know what Bessel's equation is?
Oh, no, I don't know it anymore.
Catherine?
I don't know it precisely. There's like a second derivative term and a first derivative term, and then
well done. It's a second.
I don't remember the rest.
That's great. No, but actually that's a good start. Who knows where it comes from? This is the more interesting thing.
Like spherical harmonics.
Yeah, that's right. Or cylindrical harmonics also. And it comes up all the time when one's studying Laplace's equation in higher dimensions. So let me explain where it comes from by looking at how the Laplacian, what the eigenfunctions of the Laplacian look like. Here's the eigenfunction equation. What they look like on the unit disk. So this is, if you like, this is a bit of a cultural aside, but it's motivated by our interest in the Green's function and capacity, which is the topic we're going to finish today. So I just want to, the first thing to do when studying this, the eigenfunctions is let's look for functions just depending on the radius. In other words, just depending on the absolute values of z, such that the Laplacian of f plus lambda f is equal to 0. So it's an eigenfunction with eigenvalue minus lambda, and f restricted to the circle should be equal to 0. Okay, so to do that, what we need to know is what is the Laplacian in polar coordinates? And I just looked up on the web a typical answer to the question, what is the Laplacian in polar coordinates? And the calculation is just terrible. And the reason it's terrible is because if you just take the Laplacian in Euclidean coordinates and try to change coordinates, you have a lot of calculating to do. But it's so much easier if you know that d star df is the Laplacian of f times the area form, which is r dr d theta. So all we have to do is calculate d star df. So let's do that in the case of a radially symmetric function. So it only depends on r. So df is equal to the derivative of f with respect to r. I'll write this as f sub r dr. And then when we take star of that, it just changes the dr to r d theta. And now we want to take d of that. So we just have to take d of frr d theta. And so that's the second derivative of f with respect to r using the Leibniz rule for this product. Just take its r derivative because we have a d theta here, plus, and then we differentiate the r, the r becomes 1, and then we have dr d theta. But what we really wanted was r dr d theta, which is the volume form. So we put r here and then divide this by r and erase this r, put this in parentheses. And then this is the Laplacian of f. Pretty easy. So the Laplacian of f is just the second derivative with respect to r plus 1 over r times the first derivative. And now if you want to satisfy this eigenvalue equation, that gives you the equation d squared f dr squared plus 1 over r df dr plus lambda f is equal to 0. So let's try to start out with just lambda is equal to 1. Let's ask ourselves if we can understand what the solutions to this equation look like. So this is an ordinary differential equation in of degree 2, so it should have 2 linearly independent solutions. But it's a little bit strange because it has this 1 over r in it. So something funny happens at 0. So it turns out that this differential equation, this is the the simplest instance of Bessel's equation. It turns out that this differential equation has two linearly independent solutions, and they're normally called y0 of r and j0 of r. But y0 of r blows up at r is equal to 0. And so it's not going to give us something that came from a smooth function on the disk. So what we're really interested in is the other solution, j0 of r. And this solution, j0 of r, has a beautiful form. First, it's normalized, so it's 1 when r is 0. And then it comes down and goes up, and goes down and goes up, and it oscillates. It's well defined on the whole real axis. It can be extended to a meromorphic function in the complex plane. And it has zeros at certain locations that we'll write down. Just call them alpha 1, alpha 2, alpha 3, alpha 4. It has zeros going far off to the right. Now, what does this function look like when r is large? What does it look like on the board?
Cosine function?
Yeah, it looks something like cosine, right? In fact, cosine is a good match for it because cosine is 1 here, and then it goes oscillating like this. And in fact, this is asymptotic to a multiple of cosine. And the reason is that when r is large, this term barely matters. This first derivative term in f goes to 0. So you just have the second derivative of f is minus f. And its solutions are sine and cosine. So in fact, the difference between the zeros, between successive zeros, converges to pi as n goes to infinity. And this looks like a decaying cosine wave as you look far to the right, but these zeros are not in any exact position. There's no closed form for the locations of the zeros. But now how do we get functions on our disk? So we want to make a radial function that goes like this, but we want it to vanish on the boundary of the disk, right? Because that's what the Green's function is doing. It's finding the solution to Laplace's equation that vanishes on the boundary of the disk. So we want to scale our function so that it vanishes when r is equal to 1. So what we look at is j naught of alpha n times r. So that when r is 1, this is one of the zeros of j naught. And then some of the eigenfunctions of the Laplacian are just fn of r is some constant depending on n to normalize them to have norm 1 times j naught of alpha n r, where alpha n is the nth zero. So that's just to give you a glimpse of what these eigenfunctions look like on the unit disk. They come from Bessel functions. And it's quite interesting to just compare this to if we wanted functions on the interval, say from -1 to 1, that depended only on the absolute value of x and were eigenfunctions of the Laplacian, then what we could do is we put in something like this. In other words, we could exactly take cosine of beta nx to get the corresponding things in one dimension, where beta n is the location of the zeros of cosine. So 2n plus 1 times, n plus a half times pi times pi. So it's one of the beautiful features of both the disk and the interval is that these eigenfunctions of the Laplacian are built from a single function by rescaling it in space. And the zeros of the function tell you how to scale, and they tell you what the eigenvalues are. The eigenvalue of this is turns out to be minus alpha n squared. Okay, so that was just a cultural aside about the Green's function. Now, how are we using the Green's function for capacity? We're using it to define the capacity of an arbitrary compact set in the plane, initially starting for one where we can solve the Green's function on the outside. So maybe this is a good moment to introduce a word I should have defined earlier, full. So we say K, a compact set in the complex plane, is full if both K and the complement of K are connected. The complement we usually denote by omega. And so K is all in one piece. It might look something like this. And if it has it only has one component to its complement. So you have to fill in any holes that K might have. It's not allowed to be, for example, a circle, because a circle would give two components in the complement. That's why it's called full. You fill in all the holes. And when it's full, then the complement is simply connected. Pi 1 of sigma is trivial. And we have a Riemann mapping to the complement provided K is not a point. So let's just suppose for the moment that K is full, then we have a Riemann map from the complement of K to the complement of a disk of some radius, closed disk of some radius, with f of z near infinity equal to z plus a bounded holomorphic function. And so this is for absolute value of z large. And then we define R to be equal to the capacity of K. And if in the event that K is a single point, which is technically a full set, then R is equal to 0. So the capacity of a point is equal to 0. So that's the idea of the potential theoretic definition of capacity. But there's a different way of looking at it in terms of the Green's function. So I'll remind you that the Green's function for K is harmonic on omega. It's restricted to K, it's equal to 0. And for large z, it's just the log of the absolute value of z, and then plus a constant, plus terms on the order of 1 over the absolute value of z. So remember, being harmonic, it's almost the real part of a function that's holomorphic at infinity. And in fact, this part here is the real part of some g of z, which is holomorphic at z equals infinity. So it's a constant plus terms that converge at infinity, we go to 0 at infinity. And you'll notice that we've normalized so that g restricted to K is equal to 0. And then we also have that the Laplacian of g is 2 pi mu, and mu is the equilibrium measure. Now, in the case over here, it's easy to see what the Green's function should be, because we know what the Green's function is for the complement of the disk of radius r. So it should be 0 on the disk of radius r, and otherwise it should grow logarithmically. And then we just pull that back by our Riemann mapping to get the Green's function for K. And so the Green's function over here is given by log absolute value z, but then we have to divide by r so that it's equal to 0 on the circle of radius r. And so when we pull that back, we get that g of z is equal to log of the absolute value of f of z minus log r. And since f of z is normalized, so it's been normalized to osculate the identity at infinity, this is equal to log of the absolute value of z minus log r plus terms of order 1 over z. And so this quantity here is gamma. And that shows us that in the case of the full set, the capacity of K is just equal to e to the minus gamma. Okay, so the capacity of K for a full set should be thought of as the size of a round disk that's conformally equivalent to it, in the sense that their complements are conformally equivalent by a map that's close to the identity at infinity. And that definition works in general because you see we don't need K to be connected to define its Green's function. The Green's function is defined whenever we can solve the Dirichlet problem on the complement of K. So this definition works in general. Here's another way to think about the definition. If you take the equilibrium measure and you convolve with mu, then you get a, you take our fundamental solution for the Laplacian, which is E of z is a log of the absolute value of z, and you form E star mu, you'll get a harmonic function phi normalized so that phi of z is equal to log absolute value z plus O of 1. Plus little o of 1, plus big O of 1 over the absolute value of z. So in other words, normalized so this constant term isn't here. So when you form E star mu, then its values, what you've done is you normalized it at infinity rather than normalizing it at on the boundary of your set. And so the difference between E and G is harmonic. And therefore, it's also bounded, so it's just a constant, and the constant is this constant gamma. So E star mu, that is the potential that we cook up just using the equilibrium measure, is equal to minus gamma on K. And so if you like, the other way to think about this constant gamma is you find the equilibrium measure, then you take its potential, and then you look at what its boundary values are. And e to those boundary values gives the capacity of K. So this potential and the Green's function are the same up to a normalization. The Green's function is normalized so that G restricted to K is equal to 0. And this potential is normalized so that it has no constant term at infinity. You can't do both of those normalizations at once unless the capacity is equal to 1. Okay, so last week we proved that there's some other ways of measuring the size of a compact set. For example, there's the polynomial radius, and then there's the transcendental diameter, and then there's our new radius called the capacity, and the theorem is that these all three are equal. So let me just finish the proof of that theorem. So this part we already proved using van der Waals determinants, and actually we proved the first half of this, but I'll review that. So the proof of star. Okay, so let me remind you what R, sorry, it's not this part, it's this part. We're going to prove that R infinity equals the capacity of K. So R infinity of K. And I'll remind you, this is the limit of R n of K to the 1 over n. So we're going to prove that's the capacity of K. And Rn of K is the minimum over monic polynomials of degree n of the maximum over K of the size of the polynomial on K. And little rn, what we're really interested is this to the 1 over n power. So let me put that in here. That's little rn. And that is the same as putting a 1 over n here. Now, why do I like to put the 1 over n there? Well, suppose Pn of z is, suppose we know what the zeros are of this monic polynomial. They uniquely determine the monic polynomial. Then the absolute value of Pn is just the product of these absolute values. And the log of the absolute value of Pn of z to the 1 over n is almost a harmonic function. Let me call this Pn. So what is it? Well, it's the sum, it's 1 over n times the sum of the logarithm of z minus ai. But the logarithm is our fundamental solution to the Laplacian. So this is the same thing as the convolution of E with the measure mu n, where mu n is a probability measure. It's just 1 over n times the sum of the delta masses at the zeros of P. So this is the reason why polynomials and potential theory are so closely related. It's that in the case where if you want to cook up a Laplacian and it's the corresponding measure, the charge distribution consists of equal charges at a finite set of points, the corresponding potential is just the absolute value of a polynomial up to a constant, which is this 1 over n. So that's why we can compare, why you think there might be some comparison between the capacity and the values of polynomials. So we have this interpretation of the normalized absolute value, or at least its logarithm, as a harmonic function. And this harmonic function is equal to log absolute value z, because this was a probability measure. We have n terms here, so it's near infinity. The AIs make little contributions. Log absolute value z plus big O of 1 over the absolute value of z. Okay, so now we're trying to relate that to the capacity of K. Now both sides scale correctly, so we can dilate K to reduce to the case where the capacity is 1. So we can assume that the capacity of K is 1. So then the Green's function of K is log z, and now this gamma is 0, plus big O of 1 over the absolute value of z. Okay, so now what you'll notice is that here we have a harmonic function that behaves the same way at infinity as the Green's function does. To high order, even the constant term is missing. They both, if you get rid of the log z, they both vanish at infinity. So if we look at g of z, actually let me put it this way, if we look at phi of z minus g of z, and sorry, this is phi n of z, corresponding to a monic polynomial of degree n, this is equal to big O of 1 over the absolute value of z. And it's harmonic. So it's harmonic on omega, and so it equals 0 at the point infinity. Okay, so here's our set K. Here's the point at infinity, and we have this harmonic function. This difference vanishes at this point. So we have a function that's equal to 0 here, and it's harmonic outside. So what can we say about its values on the boundary of omega? Well, by the mean value theorem, if you have a function, a harmonic function that vanishes in the interior of the region, its maximum on the boundary has to be bigger than or equal to 0. And its minimum on the boundary has to be bigger than or equal to 0. Otherwise, we would be attaining the maximum inside. So this implies, by the maximum principle, that phi n of z minus g of z is greater than or equal to 0 for some z in the boundary of the domain at infinity. But g vanishes on the boundary. That's the definition of the Green's function. So that says phi n of z is greater than or equal to 0. But phi n comes from the logarithm of Pn to the 1 over n. So no matter what polynomial we choose, the log of its absolute value is greater than or equal to 0 at some point on the boundary. That means Pn itself is greater than or equal to 1, which means Rn of k is greater than or equal to 1. So this implies Rn of k is greater than or equal to 1 for all n, and so that implies R infinity of k is greater than or equal to 1. Okay, so that's one direction of the comparison. How do you do the other direction? For the other direction, we need to construct polynomials that behave well. So what do? Well, we're free to choose where the zeros are. Where should we put the zeros? Well, the zeros are going to create a measure. And there's a measure sitting around that we'd like to use, which is the equilibrium measure. The equilibrium measure would reproduce the Green's function when we form this convolution. So if we take measures that approximate the equilibrium measure, then the polynomials will approximate the Green's functions. These phi n's will be close to g of z. So for the other direction, we choose the ai from 1 to n. So the corresponding measures converge to mu, which is the equilibrium measure. Which is, and g is E star mu. And phi n is E star mu n. So as you would expect, phi n tends to g. But in what sense do they converge? Well, we're taking these functions that blow up at the AIs. They're very badly behaved near k. What we're doing is we're putting we're taking measures that somehow give finite approximations to the equilibrium measure, which is this nice charge distribution on the boundary of k. We're replacing those by point charges, and we get these potential functions which go off to minus infinity at those points. And the Green's function vanishes on this set, so it's certainly not going to get uniform convergence on k. But that's because we have singularities at these points. As long as we stay away from the singularities, we get uniform convergence. So this convergence of phi n to g holds uniformly on compact sets inside of omega minus k. Not on k itself, but on compact subsets thereof. And so now we're almost done, because you see, here's our set k, and we have the level sets of the Green's function, which the Green's function is equal to 0 on k. So what we do is we choose a level set of the Green's function. We look at the locus where g is equal to epsilon, which is a small number. And this defines a compact subset of omega minus k. And g is identically equal to epsilon here. So we then choose capital N so that phi n minus g is itself less than epsilon on the set where the absolute value of g is epsilon. So since this was compact, we can arrange that phi is also close, phi n is also close to epsilon there for all n bigger than big N. And so now phi n is an absolute value, well, it's just in value, less than or equal to 2 epsilon on this set. Okay, so now we have this harmonic function, which is, and this is harmonic in the whole complex plane apart from the zeros of the corresponding polynomials. it's bounded by 2 epsilon here, and then there's these zeros on k, and it tends to minus infinity at the zeros. So by the maximum principle, phi n is bounded above by 2 epsilon on k. So this implies phi n restricted to k is everywhere less than or equal to 2 epsilon. But remember, this was just 1 over n log absolute value Pn. And so that shows that the log of the absolute value of Pn, at least divided by n, that the sup of this over k is less than or equal to 2 epsilon. And so the sup of this over k tends to 0 as n goes to infinity. And these quantities are just the logarithms of the Rn of k. So if the log of Rn of k go to 0, then the then R infinity has to converge to be equal to 1. Okay, so this shows that not only do the polynomials that we're getting approximate this equilibrium measure, sorry, what I want to say is not only do the invariant we get from polynomials is the same as the invariant we get from potential theory, but it tells us that to get the best polynomials for k, what we should do is find polynomials whose zeros approximate the equilibrium measure. And so somehow there's a close connection between these polynomials and the Riemann mapping in the case where k is full. And we're going to see an instance of that in just a minute. Okay, so that was the main thing I wanted to establish theoretically about capacity, that there's 3 natural measures of the size of sets in the complex plane, and they all coincide. Now, what good is it to have 3 different definitions of the same thing? Well, we already saw one application, which is that when you're trying to compute the capacity of k, you can use either of these 2 definitions, and explicit choices of sets of points in k give upper and lower bounds depending on which of these 2 things you compute. So having these 2 definitions in play allows one to get concrete upper and lower bounds. Here's another application. Suppose I have a compact set k. Maybe it's a tree with fruit, who knows? I'm drawing it as if it's full, it doesn't have to be. And I take it and I just project it to the real axis. So then if it's connected, it'll just give me an interval along the real axis. Maybe it's disconnected, maybe it gives me a Cantor set. In any case, I can ask, how does the capacity of k compare to the capacity of k prime? Well, projections are contractions. So it looks like the capacity of k prime is smaller. But if you were to go back to the Green's function definition, you'd find it very hard to prove that. Because it's hard to say how to take the Green's function for k and relate it to the Green's function for k prime. On the other hand, if you look at this definition of the transfinite diameter, remember the transfinite diameter has a long definition. In the middle, there's a product of ai minus aj. Well, if you project the points ai on k to the real line, they get closer together. So this is greater than or equal to the product that you get when you use the projections. And so the transfinite diameter obviously goes down. And therefore, since everything's equal, the capacity goes down. So the capacity of k prime is less than or equal to the capacity of k. So that's a typical comparison that would be hard to prove using potential theory, but is easily proved using this equality of different definitions. The next thing I want to observe is that if the projection were an interval, that is if k were connected, then we know exactly what the capacity is. the capacity of the interval on the real axis from A to B is exactly B minus A over 4. It's the length of the interval divided by 4. How do we know that? We know that because we know one example. The capacity of the interval from -2 to 2 is equal to 1 because the Riemann mapping from the unit disk to the outside is given by z goes to z plus 1 over z. So that mapping sends the unit disk to the outside of the slit from -2 to 2. And therefore, this has the same capacity as the unit disk. And so it must be equal to 1. And then since the capacity scales when you dilate a set, and of course it's translation invariant because this definition only involves distances, it's evident that for a general interval, we just get the length of the interval divided by 4. Now, where else have you seen the quantity divided by 4, say 1 divided by 4, in our discussions of conformal geometry?
Was it like the 1/4 circle theorem or something like that?
That's right. So there's something called the Cuba 1/4 theorem. So by the way, let me sum up this discussion by making the following point. So as a corollary of this discussion, we have the following little theorem. If K is connected, then the capacity of K is less than or equal to the diameter of K divided by 4. Because the diameter is just the minimum distance between 2 points. If we find 2 points that maximize that distance, then we just project onto the line through those 2 points. And by the same argument, the size of the set only gets smaller, and the image at least contains an interval of length the diameter of K. It contains an interval of length exactly the diameter of K over 4. Diameter of K, then we divide by 4 using this calculation I just erased. This one here didn't erase. Okay, so we know an upper bound on the capacity of connected sets. And so now as a corollary, I want to go back to this theorem called the Cuba 1/4 theorem. And let me remind you what it says. Suppose we have a Riemann mapping that's been normalized. It's z plus a2z squared, so on. It belongs to this class S, which just means F gives a 1-to-1 map from the unit disk into the complex plane, sending, of course, 0 to 0, and with F prime at 0 equal to 1. Then the Cova theorem says, so let F be this, then the image of the disk contains the ball of radius 1/4 at the origin. And here's our new proof. So here's our Riemann mapping. It sends 0 to some set. So this is the image of the disk. And what we're interested in when we're discussing capacity is not so much the image of the disk, but the outside of the image. So we let L be the Riemann sphere with the image of the disk removed. That's compact. This is open, so its complement is closed. And then we look at 1 over L and call that K. So by 1 over L, I just mean take the reciprocals of all of the elements in this set. So what is if this is L, what does 1 over L look like? Well, the point at infinity goes to 0, so it certainly contains 0. And it's connected. So that's the reciprocal of this set. It contains 0 and it contains some other stuff. So let's suppose we have a point P that's in L. Then 1 over P is in 1 over L. Okay, which is K. So K contains 0, and it also contains the point 1 over P. Now, what is the capacity of K? Well, you can see what it should be from here. You see, if we take the mapping, if we want to get a mapping from the outside of the unit disk to the outside of K, we just take Z goes to F of 1 over Z, and then we take the reciprocal again. And that mapping oscillates the identity at infinity because of the normalization of F to oscillate the identity at 0. And so the capacity of K is equal to 1. Okay, so for any Riemann mapping normalized in this way, the complement of its image has the property that its reciprocal has capacity 1. Well, if its reciprocal has capacity 1, then its diameter is at most 4 by this. Did I do this backwards? Yeah, the capacity of K is greater than or equal to the diameter of K over 4. So 1 over P must be less than or equal to 4, since the capacity of K is 1, and so P must be less than or equal to, greater than or equal to 1/4. So in other words, any point in the complement has to have absolute value bigger than 1/4. Otherwise, the reciprocal of the complement would have capacity that's too large. And so that proves that the points of size less than 1/4 must be contained in the image, which is the Kubo 1/4 theorem. Okay, so this is a different way to look at the Kubo 1/4 theorem. And in fact, there's a theorem which we don't have time to prove, but which is in fact, more or less obvious from what I just said, which is that if you have 2 points, A and B, and you want to make a connected set that contains both of them, and you want its capacity to be as small as possible, you can just take it to be the line segment between those 2 points. Okay, so let me finish up with maybe 3 or 4 remarks. So something I didn't develop, but which could have been developed, was the idea of energy. So if we have a measure mu on C, let's say with the support of mu contained in K, which is compact, then we define the energy of mu to be the integral over K cross K of the log 1 over Z minus W, using the measure mu to pick out the coordinate Z, and then the same measure to pick out the coordinate W. Well, what is this energy telling you? This quantity here describes the potential energy at Z induced by a point charge at the point W. So you think of this measure mu as being a charge distribution, like maybe it's a finite set of electrons. As you try to bring them into this compact set K, you have to do work. It takes a certain amount of energy to bring these points together because they repel each other. How much energy does it take? Well, that's what I of mu measures. It measures the energy required starting with charges at infinity to bring them together and confine them to this compact set K in the positions given by mu. Now, I should say that that's a bit of a lie, because the energy required is actually infinite. But this is a kind of renormalized energy. It's allowed to take negative values, and it still has the right intuitive meaning. And so the theorem here is that given K, the energy I of mu is minimized by the equilibrium measure. And the capacity of K is E to the minus that energy. So in fact, we could have started our whole discussion by discussing the equilibrium measure rather than the Green's function, which maybe seemed a little peripheral. let me just at least justify this formula here. So for example, when the capacity of K is 1, G is equal to E star mu, and it's equal to 0 on K. But you see, if you integrate with respect to Z here, this integral with respect to Z gives the convolution of E with mu up to a sign. So it gives minus the Green's function, which vanishes on K. And so when you integrate with respect to W, you're just integrating 0 with respect to W. And so you indeed get energy 0 exactly when the capacity of K is equal to 1. Okay, so that's another element of the picture about capacity. The second thing that I would be really remiss not to mention is that there's another interpretation for the equilibrium measure. So here's our point at infinity. Here's our compact set K. Remember, a long time ago, we discussed the idea that if you have a set A on K, you can look for a harmonic function that's 1 here and a 0 on the rest of the boundary, and then see what its value is at a given point, say infinity. That value was called the harmonic measure of the set A. So in fact, the equilibrium measure of a set A, where A is contained in K, is exactly the harmonic measure as seen from infinity through the domain omega of the set A. So in fact, this equilibrium measure, at least in the case where K is a finite union of Jordan domains, is exactly this harmonic measure that we've already discussed. So that's another entry into the description of capacity, maybe through more familiar ideas. And this is easy to see in the case where K is full. You can just use the Riemann Mapping theorem to compare the harmonic measure on the boundary to what I defined as the equilibrium measure. Everything is very explicit in the case where you have a Riemann mapping. Okay, and the last thing is that I mentioned this, that when K is full, these good polynomials, Pn of Z, can be chosen. So first, the corresponding Rn to the 1 over n converge to R infinity of K. Second, the zeros of Pn are contained in K. And finally, Pn of Z to the 1 over n converges to F of Z, which is the Riemann mapping from the complement of K to the complement of a disk of subradius. Let's do this in the case, again, normalized, where the capacity is equal to 1. Then these converge to the Riemann mapping from C minus K to C minus the disk of radius 1. Now that should worry you because I'm taking the nth root of a complex number here. But don't worry too much because remember we're the complement of K, when it's full, the complement omega, which is this with infinity thrown in, let me put C hat on both sides. This complement omega is simply connected. So if we have a function that's nowhere vanishing, and it is nowhere vanishing because the zeros are in K, they're not in omega, then we're able to extract an nth root of it. To be more formal about it, remember this is monic of degree n. So this quantity is z to the n plus, etc., to the 1 over n. And we can write that as z to the n times 1 plus, etc. And then when we take the 1 over nth power, we just get z here, and then we get 1 over n applied to this non-vanishing holomorphic function. So again, the logarithm of this function can be well defined on a simply connected region. And so we can form 1 over n consistently by normalizing that its power series should start with z at infinity. So there's a beautiful relationship now made precise between these polynomials and these Riemann mappings. And this relationship arises very naturally in complex dynamics. So the last thing I want to say about complex dynamics, about capacity, is this relationship. So for example, I want to consider iterating a polynomial on the complex plane. And again, to keep things simple, I'll choose the polynomial to be monic. So let's let f of z be z to the d plus a1 z to the d minus 1 plus ad. Be monic in a degree greater than or equal to 2. And a good example to keep in mind is just z squared plus a constant. Z squared plus a constant is already a very rich family of dynamical systems. Now, how does the iterates of f behave? Well, what happens is there's a full set that is a set whose complement is connected, called the filled Julia set of f, which consists of the points that stay bounded under iteration of f. For example, the periodic points of f. We've talked about this very briefly before. And then if you pick a point outside of k of f, it goes off to infinity, and eventually very rapidly, because when you take a large number and you raise it to the dth power, it's much larger, and these terms are insignificant because z is large. So this k of f is defined to be the set of z such that as you iterate this polynomial, you do not converge to infinity. That is, these points stay bounded. And it's easy to prove that k of f is compact, because if you take z very large, it does go off to infinity. And it's also full, that is, the complex plane minus k of f is connected. And of course, the most interesting case from our perspective is where k of f is connected. Because if k of f is also connected, then there's a Riemann mapping to the outside of k of f, and we could try to explore what it is. Well, it turns out there's a simple criterion for k of f to be connected. Namely, k of f is connected if and only if all the critical points of f are in k. As long as the branching behavior of f, that is the zeros of f prime, remains in this set k, there's no way for the set k to sort of tear apart. Or there's no way for the basin of infinity to not look like a disk. And so in this case, there exists a Riemann map. A little f from the complement of k of f to the complement of the unit disk. And now there's a beautiful theorem. What is this Riemann mapping? Here it is. It's the limit as n goes to infinity of f to the n of z to the 1 over d to the n. So notice that this is of the form that I alluded to in general just a moment ago. Namely, f is a polynomial of degree d. When you iterate it, compose it with itself, once it becomes a polynomial of degree d squared, because z to the d to the d is z to the d squared. When you compose it with itself n times, it becomes a polynomial of degree d to the n. So this is just a polynomial. And in fact, it's a monic polynomial because f was. And we're taking this monic polynomial and we're taking a large root of it, the root being equal to the degree. So this, in fact, is simply this limit looks like z plus O of 1, at least for large values of z. So we can explicitly compute the Riemann mapping. And what does this Riemann mapping do? Well, it's very pretty. We have this set K and this dynamics of F going on. And over here, we have the unit disk. And then we have this Riemann mapping defined on the outside of K of F. And of course, outside the unit disk, iterates under the dynamical system z goes to z to the d also go off to infinity. So what happens is the Riemann mapping conjugates the dynamics of this polynomial to the dynamics of z goes to z to the d. And you can see that directly from this formula. That is, if we take f of z, so we go over first and we raise it to the dth power, that's the same as first applying capital F to z and then taking the image of that. So F conjugates the dynamics on the basin of infinity for capital F to the dynamics of z goes to z to the d on the basin of infinity. It turns this very complicated dynamical system into this very simple one. And then, if we wanted to know what the Green's function is for this polynomial capital F for its Field-Julia set, we would just take the circles of constant radius centered at the origin here and pull them back, and those would be the level sets of the Green's function. So the Green's function would come by taking the logarithm of this formula. That is, the Green's function, or K of F, is g of z is the limit as n goes to infinity of 1 over d to the n log absolute value Fn of z. Now here's one of the beautiful things about this formula. This formula makes sense whether or not K of F is connected. Here we use the Riemann mapping. We can only take these roots if this function was null or 0. But here, we just have to take the absolute value of the iterates. That makes sense no matter what properties K of F has. The points that go off to infinity eventually get very large, and one can easily show that this limit exists. And in fact, this is the Green's function independent of whether or not K of F is connected. And so as a corollary of this, as we can see in both cases, the Green's function near infinity looks like log z plus O of 1 over z. Or the Riemann mapping goes, when normalized, goes to the unit disk, not the disk of some strange radius r. So as a corollary of this, we get that the capacity of K of F is equal to 1 whenever F is monic. Okay, so monic polynomials give rise to very complicated sets where we, for some strange and beautiful reason, where we can explicitly compute the Green's function and the Riemann mapping when it exists, and the capacity comes out to be very simple. Okay, so I'm going to show you a picture, but let me just ask, let's propose the following problem. You get us an assignment on the homework. It says, draw a picture of K of z squared plus I. So how can you do that? Well, you could try to find points whose orbits remain bounded, but that's going to be a real pain. What's easier to do is to try to compute the outside of this set. So what you can do is you pick points at random in the complex plane and you compute the Green's function for them. And this Green's function makes sense for every value of z. And if it happens to come out to be 0, then you were in this set. But if it comes out to be small, then you were close to being in this set because the Green's function is close to 0 near K. And see, it might be the case, and in fact it is the case, for this polynomial that k has measure 0. So if you pick points at random, you're never going to find k. But what you will find is points where the Green's function is close to 0. So the problem of how to draw a picture of the Julia set has the following solution. You don't draw a picture of the Julia set. What you do is you color points in the complex plane according to the value of the Green's function. And when the Green's function is small, you color them, I don't know, so that it's close to black, and you color the points where it's 0 actually black, or gray maybe, so that you can see that they're in the Julia set. So, so in that way, instead of just drawing the Julia set, you solve a harder problem, which is you also draw its Green's function. And this is what everybody does when they draw pictures of Julia sets. So let me go back to this picture, which we've seen earlier several classes ago, several lectures ago. This is the Julia set of a quadratic polynomial. It's been carefully chosen so that its critical point not only does not go off to infinity, its critical point is at the origin because it's z squared plus c. Its critical point is in a cycle of order 5. So it certainly has a connected Julia set, which is this white region here. Now what's on the outside? The outside is colored according to the value of the Green's function. And so these level sets here, these black curves, those are literally the images of circles of constant radius under the Riemann mapping to the complement of this set K. And they're very easily computed, and they can be computed very rapidly. And these points that are colored black are points where you pick a pixel to examine, and it's not actually in the Julia set. Its center is not in the Julia set, but you can prove that there is a point in the Julia set inside there because the Green's function is so small. So you color those black, and those are on the frontier. They're on the boundary of the filled Julia set. And then there are some points where the center of the pixel is definitely in. It has a bounded orbit. And so those get colored white. So that's the coloring scheme in this picture. On the outside, it's shaded by the Green's function. Where points are definitely bounded, they're shaded white. And where the Green's function is very small, so small that you know that the boundary of the Julia set is, of the filled Julia set is in your region, then you color it black. This boundary, by the way, is maybe the more interesting set. That's a set of Hausdorff dimensions strictly between 1 and 2, and it's sort of self-similar. And this is exactly where the harmonic measure lives, or the equilibrium measure. The equilibrium measure is supported on these black points here. It's supported on the ends of, on the boundary of the set K. Okay, so that was a little bit about the connection between capacity and Green's functions in complex dynamics. And I think the main thing of interest there is really that all of these kind of exotic sounding objects that are maybe constructed using an abstract solution to the Dirichlet problem can be found and manipulated completely concretely in cases where the sets are very exotic if they happen to have a dynamical origin. For those of you who are taking Laura DeMarco's class, or maybe even more for those of you who are not taking Laura DeMarco's class, there's something very tempting to do if you're interested in number theory, which is to examine the case where, say, this polynomial is in, I don't know, maybe Q adjoins Z, or its coefficients lie in a number field. Let's say it's Q, though. Then instead of looking at the absolute value of this quantity, well, if Z is itself a rational number and F is a rational polynomial, then this is a rational number. And so instead of using the ordinary norm here, you can look at the p-adic absolute value of F to the n of Z. And it turns out that this limit also exists. And so one gets an analog of potential theory over the real place of Q that makes sense at every prime. And that has a lot of arithmetic consequences for dynamics, and indeed it feeds back into questions in number theory that have no initial dynamical content. Okay. So this concludes the discussion of capacity. Are there any questions before we proceed from here? Okay, so let me just give you a heads up about the trajectory of the course. This course has a wellness day coming up, which is next Tuesday. Everybody will be off. You don't have to come to class. Class will not meet. And next class, I will talk about extremal length, and that will be the last topic in the general theory of conformal invariance. So we will be finishing up with our final conformal invariant, extremal length. Then we'll have a break of a week. And then when we come back, we'll be starting on random processes in the plane. So I encourage you, and I'll say this again next time, in preparation for this kind of shift in the focus of the course, to look at the book by Dinkin and Yuskevich. This is also referred to in the course notes. So also look at the course notes, the chapter called Random Walks. Because we will shortly be making a kind of change in emphasis in the course to discuss random processes on lattices, and then we'll reconnect that to potential theory. And in addition, we'll have this break where Tuesday is off. Okay, so let me then start on this final topic, which is extremal length. Okay, so before I address this topic, let me give you a typical problem that it can be used to solve. So there's a theorem that says let A contained in the Riemann sphere be a doubly connected region. This means either that pi 1 of A is isomorphic to Z, or equivalently that C hat minus A has two components. Then A is isomorphic to the punctured disk, the complex plane, or the standard annulus of radius R, which is the set of Z such that 1 is less than the absolute value of Z is less than R. Okay, so we'll start by proving this classification of doubly connected regions, which is pretty easy once you have the Riemann Mapping theorem. But let me give you an example. So suppose you take the square of side 1, and you put it inside of a square of side length 4. Everything's centered here. So S4. Then this region here, between the square of side length 4 and the square root of side length 1, is a doubly connected region. Its complement in the Riemann sphere consists of this square and the outside of the big square. Or its fundamental group is Z. It's generated by a loop that goes around the inner square. Now this theorem says that this region between these two squares is isomorphic by some conformal map to a standard round annulus. So the region between the circle of radius 1 and the circle of radius R. And in fact, the value of R for which this works is unique. So there's an invariant of this region not all annuli are equivalent. When you draw an annulus in the plane, it's equivalent to some specific radius r. And the map that goes from here to here is transcendental. It's quite hard to get your hands on it. It would be hard to write down explicitly. But that's not what I want you to do. I want you to not figure out exactly what r is, but to estimate r. It seems pretty obvious that this annulus is not conformally equivalent to a tiny one, radius 1 plus epsilon, and it's not equivalent to a huge one, say where r is 100. So how can one get good estimates for the radius of the standard model for a non-standard annulus? And that's what the extremal length method of extremal length will allow us to do. And it's particularly robust when applied to problems like estimating the modulus of an annulus. And also there's something called a quadrilateral, which is kind of like a distorted rectangle. So if you have a quadrilateral like this, it turns out it's conformally isomorphic to a rectangle. Say where the lengths of the sides are A and B. And given a concrete cube, the problem would be here to estimate the ratio B over A. Okay, so that's the topic we'll start on next time. And then we'll be ready to wrap up conformal invariance and move on to random walks. Okay.